Alright, hey guys, give me a quick sound test. Let me make sure you can hear me, and then I'm going to turn this over to Scott. Hey Amber. Hey Tom. Wilda, thanks. Jen, alright, cool. It's all yours, Scott.
Okay, and I guess I ought to make a quick check and make sure my audio is fine also, and I also want to make sure everyone can see the front screen. You should be seeing a picture with the list of the winning lottery numbers for this week, so if you don't see that, you're probably missing a huge opportunity.
I don't see it.
Okay, I'm just kidding. All right, on to week 2 nitty-gritty, guys. But first, before we begin, as always, we want to make sure, are there any questions any of you have that should be addressed? Anything you thought of after last week or as you were working on some of the designs for your own creatures? Which, by the way, I went to the forums. I did get to leave some comments yesterday, and there's some really cool stuff going on there. If any of you haven't gone, you should definitely go back and see what your comrades are doing. All right, well, it looks like we don't have any questions, so let's leap into it. Oh, go ahead and save your question about skin covering till later. That's some of the nitty-gritty we'll be covering today. But the short answer is that dinosaurs do have protofeathers, and, well, you'll see what they are. I have slides. You're welcome, Tom. All right, then. On we go. So today we're going to cover a little bit of a surprise. Several of you asked about mussels last week, and I said we probably didn't have time to do a proper overview of mussels, and we don't, because that would take the entire class. But I am going to try to cover or touch upon some of the most important mussel contours, especially ones that are fairly universal to creature design, and that you can look at some commonalities and differences between mammal-like creatures and dinosaur-like creatures. So we're going to look at that. Surprise, bonus material. I also want to look at snakes really incredibly briefly, because I saw there was one design with a guy doing something cool with snakes coming out of something. And snakes are more complicated than most people look at, so I want to cover them really briefly. And then we're going to get back to finishing up some issues with legs that we started touching upon last week and also covered a little bit in the free webinar. And then we're going to look at things that happen on the real nitty-gritty, things that happen on the mouth end, beaks, lips, and teeth. We're going to look at eyes. And we're going to finally top it off with fur, scales, and skin, and we'll talk about feathers, and I'm going to encourage you, I'm going to give you the punchline now, I'm going to encourage you not to use feathers for creature designs that take place off of our planet or are supposed to represent aliens from another planet. And then one more little bit of bonus material which will lead us into week 5. I want to look at more exotic senses, that if you're really designing something that doesn't come from planet Earth, what can you do besides the usual eyes, ears, and nose kind of senses, and what can you see on our planet that would actually show you how just a little bit of reshaking up our planet's history, you might end up with something very different looking that you can use as a design guide. Okay, so let's dive right into mussels. I really want to say, I don't know who makes these, but those are as an anatomist, I have to say those are the most awesome pants I've ever seen in my entire life. Okay, so mussels. One thing I often get questioned, and we're not going to be able to cover it in detail, but is how do we know what the mussels look like in extinct things? You know, with mammals, it's kind of obvious because we have living mammals, and with birds and crocs, it's kind of useful. The big thing is that animals tend to be very conservative with their mussels, and I don't mean like they're going to vote for Romney for sure, but rather they tend to really stay the same. All animals, since really they crawled out of the water, have had, say, triceps connecting their limb-like things to their shoulders. So like if you look at living dinosaurs, like these fairly upset birds here, and you were to dissect their muscles, well, maybe not these, but something like this ostrich, and you look at its muscles, the limb muscles, you have the quadricep equivalents up here, for example. You have some of the calf muscles down here. Those things are very consistent, not just with dinosaurs, but again across almost all animals. So if you find major markers on the bones, we are able to reconstruct them pretty accurately. One word of warning about these displays: they are incredibly awesome, as Brooks said. They really are. Everybody should go if they can. The only word of caution I will give to them is that they do randomly dissect parts out. Of course, they do that on purpose, so you can see other parts of the anatomy that would be obscured. But it can occasionally, if you're not careful, lead to an improper assumption. For example, they've actually dissected a whole bunch of the rear thigh muscles that would be going down here off. So like you could easily, looking at this, think that the thigh muscle is actually a lot shorter than it really is front to back, which should in no way dissuade you from going to see it, because it is truly one of the most amazing anatomy displays you can see. But you should be aware that they are dissecting them out a little bit. So look at it to understand sort of the inside of animals and how they work, but not necessarily where every last muscle contour goes. Of course, you could take these things too far. You can't just take chicken muscles and stretch it onto a dinosaur. So if we were going to do this as a full-blown how do we test muscles class, we would get into that EPB thing we discussed way back in the webinar, and I think briefly in week 1 also. We're not going to discuss it here, but in short, you can go ahead and map these out since they're conservatively placed, and then you can test them if one group, for example, is missing it but the other two still have it, and that lets you test whether it's a good assumption or not in the extinct group you're working on. So let's talk about muscle contours. This is a sculpture of Alamosaurus. David Krentz did it. He, of course, does dinosaur courses with Visualarium. And I actually worked with him pretty closely on the back muscles, and so I'm really quite fond of them, as you might guess. And you'll notice that rather than being totally draped on, that is, there's more meat on here than some people draw, there are these contours, but also notice that it isn't like a balloon with legs. And that seems to be like there's two schools of thought that are equally wrong. Too many people, when they restore dinosaurs and even some mammals that are extinct, either shrink wrap the skin onto the skeletons, leading to these sort of emaciated little like runway model dinosaurs, or else they go, oh, well, that's obviously wrong, we need to beef them up, and their answer to beefing them up is simply to like make them uniformly thick, which is not true either. Animals don't look like either one of those. Muscles play a really important role in how they're shaped. And we're going to talk about some of these contours specifically. So here's another dinosaur, and the ones I want to talk about first are the ones right up in here and in here, and that's kind of highlighted by these green lines here. That muscle, and you can kind of see it sliding out from underneath this other muscle we'll talk about later here, is the iliocostalis. Sorry about the name, but it actually kind of tells you what it does. Ilio means it comes from the ilium, which is the hips here, and costal, the costalis part, is ribs. And I know that's not an easy thing to memorize, but basically it's the hip rib muscles. These muscles come from the hips and run up the ribs on the outside there. And it leads to this almost platform of muscles that the back has. And there are other groups of muscles also running down there closer to the spine. And it leads in almost everything to have this nice platform. You can see it in like people who lift weights as well. You can see it in most mammals, although it's not quite as obvious. But coming forward from the hips, you'll still in most mammals see a nice contour coming up that then narrows. It's kind of beefiest in front of the hips. The reason it becomes harder to see in mammals isn't actually because it's not just as strong. It's that paradoxically, because mammals have weaker vertebrae but they're more flexible, they actually fill in all this space, when there is space, with more muscles. So basically you can't see the iliocostalis muscles quite as obviously because the other back muscles on this line are built up in order to help give them the muscles they need when they're flexing the back during running. So not perfectly round cross-sectioned animals, please. You're going to have contours coming off. See here, this area right here? This defines where the bulk of or belly of that muscle is coming up. And it literally would go running up like this from there. And then other muscles would run up here and eventually help cover it up to where the contour isn't so obvious. Okay. The other one on the torso that really should be thought of, because everything has this, again, everything that's crawled out of the water and has a backbone, is the latissimus dorsi, the lats. That's the muscle that runs from the upper arm back across the back and heads up towards the hips roughly. And you can see it here. Mammals are a little harder because we have fur and it helps cover it up a little bit, but it's a pretty obvious contour even in moving mammals because it'll ripple under the fur and all but the shaggiest of animals. And of course in animals with naked skin or tightly fitted scales, it'll be really obvious. And indeed, this is something you see in all dinosaurs, and even in some of the mummified ones you can see where the contour is here because there's a really prominent fold coming back. And I think this is important because all too often when people design dinosaurs, I think they don't know what to do with the forelimbs. So they don't have a really obvious set of deltoids or shoulder muscles. They don't have some of the muscles coming down the scapula, and they certainly don't have the lats. They instead have like pipe cleaner arms that sort of disappear into the sides. And that, of course, feeds sort of our general design consciousness. So then when we go to design some other creature and we don't want it to look like a mammal, all too often we simply sort of stick them on. We have like overly round bodies, and then we'll just have arms that sort of disappear into the round body rather than the necessary muscle contours coming off of it. One other area I wanted to cover is coming forward onto the neck. This muscle here, highlighted in red, has the obnoxiously long name of sternocleidomastoideus. Once again, it actually is named for what it connects to, the sternum, the clavicles, that would be the cladopart, and the mastoid process at the back of the skull. This is a contour that is incredibly obvious in almost everything. Of course, in people, it's quite obvious, especially when we turn our heads. It's running right up from kind of the front. It makes a V down here by our sternum and also originates a little further back and then runs up to the back of our head behind our ears. It's really obvious in essentially all mammals, but it's also incredibly, oh yeah, wanted to give Brooke props here. Her sketch and the muscles she built up in her creature in the forums shows this really, really clearly, so good job, Brooke. And it's also something that would have been really obvious in essentially everything that's ever lived on land. Here you can see the contour coming up. It would make, in the case of a lot of dinosaurs, it would be really quite flat on the bottom base of the neck, and then creates this three-dimensional change going up, and it actually inserts kind of, again, back up here behind the ear, roughly, although it sort of might disappear around from your point of view, from a sculpting point of view, close to where the jaw is, because there's some other muscles and stuff going on in there, like the jaw opening muscles. Okay, oh yeah. Let's move on actually to leg muscles, at least thigh muscles for right now. Thigh muscles are quite different once again in our mammal versus dinosaur comparisons. You already know about the tail muscles, but dinosaur muscles tend to be very sort of elongated, thin triangles in side view. And they tend to cover the entire range of the hips. Now, animals with skinnier hips, like lizards, people often think that the muscles don't cover them all because, of course, lizards have pretty skinny little hips. But ironically, the opposite is true. And I don't have a good slide of this. I have to apologize. Did anyone else lose audio before I go on?
I'm good here.
Okay. In point of fact, lizards have incredibly tiny ilia, and the muscles actually bulge off them even more. So if you were trying to add, a lot of people think, oh, if I add lizard-like muscles to my dinosaurs, it'll make them skinny. That's actually completely wrong, a misunderstanding of how lizards work. If you were to add lizard muscles to a T-Rex, the muscles would actually kind of go like this and like that before coming back in. Now, one other problem you'll often see, I don't, is that one other issue you see when people design dinosaurs, and again, I know you aren't all doing dinosaurs, although I saw someone was doing a Gallimimus. But for dinosaur-like animals as well, is there's a temptation to make the back of the knee too skinny. A lot of people, they seem to want to like split the difference between sort of the modern understanding of dinosaurs and the older, simply incorrect version. And the way they seem to solve that is to start out with really wide muscles at the top. After all, you can see the length of the hip, so you know how long it has to be. And then they like tuck the back of the thigh muscles way in close to where the leg is. In fact, this probably gets there a little too close in this diagram. It probably should come maybe just even a little bit further down. And nothing does that, and we know it doesn't do that because these muscles that go across the joint to close it actually have scars that are really obvious that are left like down here that the muscle runs to. And if you think about it, that's important because they want that leverage. The further away the point of action is, the better the leverage is to pull on the leg. And in an animal that's really big or simply an animal that wants to go fast, that's pretty handy. Is this a fold of skin? Yeah, that is. In this design, which was done during an ongoing discussion about where the leg muscles need to go actually, this was sort of supposed to be the bottom of where the tail retractor muscles for the leg went, and the yellow color more accurately reflects where it really went. So you have some sort of conflicting data between where it was sculpted there initially and where it should have gone. So basically this should be down here, and then this should be flatter on this part of the tail. It's just a little bit sticking down. You'll see another view of that that's nice in a sec. But, and this is important, even in mammals, note that in flexed-limbed animals, you don't get this skinny part of the behind the knee here. You get skinnier calf muscles, which we'll talk about later, but the muscles very much come down the leg. I mean, after all, the femur starts here and goes to the knee here, so there's a ton of distance behind the knee here. The one exception to this will be in animals that are upright with their knees almost all the time while standing, things like elephants, people, to a degree sauropod dinosaurs, and they're still extending these muscles quite a ways down the leg, but because the legs are straight, that ends up running pretty close behind the knee, so it does give you a little bit of a skinnier behind the knee look. And lizards actually do have fairly skinny behind the knees. Of course, lizards can also straighten their legs out all the way and do during locomotion. That has to do with how sprawling works. We're not going to cover sprawling much in this class, but we will revisit sprawling next week when we talk about hexapods, because all the best current known animals that use 6 or 8 legs do in fact use a kind of sprawling gait, and it'll be worth looking at in that discussion. Okay, one other thing about mammals versus dinosaurs, or scrawny tails versus big muscular tails, which we did discuss in the free webinar if you want to go back and review it in greater depth. But as a reminder, mammals have butts. They don't have anything coming out of there except a scrawny little tail like this fly swatter on the back of this horse, and of course the waste disposal system. Whereas things that are using their tails can't have the legs come together that same way, and so they tend to be very spread out. And you see that in top view really obviously. I couldn't find a good top view picture of a horse, but the muscles really do kind of come together. And of course they also round out, because this is where the equivalent of those leg-based retractors have to go. And that's all you have to pull back mammal legs, which lead to a whole bunch of changes in gait. Okay, here's a nice view, by the way, of exactly what's going on with that fold you asked about. Essentially, these big leg muscles, which again ought to be now a little lower, come down. This is also, I want to show you this because it shows you sort of how things insert into this leg muscle style. Now, if you're a more scrawnyly limbed crocodile or lizard-like animal, these muscles don't come back quite as far, and so this folding effect is not quite as obvious, but the relationship is still the same. The big tail-based muscles come back and literally bury themselves in between some of these retractor muscles that help close the knee. Oops. So some major differences on muscles and thighs in general then between mammals and dinosaurs, or a quick recap. Importantly, animal torsos are just not circles in cross-section. I don't want to be like, oh, complexity, complexity. You can definitely build them up. as you saw Ryan start to do last week, and as Brooke did a pretty good example with her mammal-like creature in the forums, you can build them up using fairly simple shapes, and you probably should when you're designing them, but the result needs to not be a balloon with limbs. That will almost always look wrong. Here's a nice long one for you. Land vertebrates, and probably things on other planets too, almost always have to have major contours on the body. And that's because, of course, you have to have the girdles, the hips, and the shoulders are really great places for muscles to originate from and then spread out across the rib cage or whatever you have in between. And so you're probably going to find that no matter how often you kind of rerun the history of life or do it on another planet in different situations. The major ones you see on our planet is the one running forward on the top of the back from the hips across the ribs. That'd be the Iliocostalis, and it has other ones which I won't name that can add other contours and help bury part of the backbone closer to the spine. And then you have another one that actually extends from the arm and goes up across the rib cage and kind of generally heads up towards the hips. And that actually, that latissimus dorsi, is essentially another sort of functional equivalent, much like the pectoralis is, for the tail-based retractors. Those are the muscles that do the most to move the arm in a broad sense. So those are pretty important muscles. Then on the neck, we also talked about the sternocleidomastoideus, or importantly, that kind of V-shaped muscle that runs from the front of the shoulders or the chest region up to the back. And that's, again, you're going to find that on darn near everything. So unless you're going to make a particularly fat or thick-skinned animal, it's the kind of anatomy that should be reflected in almost every major design for a vertebrate-like animal. And yeah, sorry about those muscle names, especially sternocleidomastoideus. It's just like, I feel like I should get a quarter every time I type it out. Okay, dinosaur thighs, wide triangles, definitely wider like in side view front to back than they are side to side when looking at them from the front or the back. And everything that has flexed knees shouldn't have the knees be too skinny. Okay, another important difference, maybe some of you can see it looking at the hind legs and side view. There's a really big difference between how mammals are put together and how dinosaurs, including birds, are put together. And it has to do this thick set of calf muscles here, which we think of as drumsticks today. These, of course, are, well, they are dinosaur, but they are chicken shins. The knee is up here, the ankle is down there. And there's this thick wad of muscle there, much thicker than you see in mammals or actually any other organisms. And that's because dinosaurs don't just have the two parts of the calf muscle or the gastrocnemius that you might see in mammals or anything else. In fact, if you've ever seen like a runner from the back in shorts, you'll notice like you can see that there's a split down the middle of their calf muscle. That's because there are two heads or two bellies, if you will, to that calf muscle. The dinosaurs have a third one that actually wraps around to the front of the knee. And it would have left an incredibly obvious contour if you were like looking at the underside in between of the legs of a dinosaur. And it's that enlarging along with the other ones that gives you that drumstick effect in, say, a chicken or in an ostrich, and certainly in any other dinosaur. In fact, this feature almost defines Dinosauria. It's found right at the base of the latest proto-dinosaurs before they become what we would technically classify as dinosaurs. And you find it in every dinosaur that ever lived, including the ones around today. Whereas mammals tend to really sort of avoid massive calf muscles and rely a lot more on the muscles of the thigh to drive that. So, quick recap. Now, I will say that drumsticks are probably, they might be pretty weird. Only dinosaurs have them, I mentioned. Nothing else seems to have produced them. So if you want to create a truly statistically normal alien, it might be best to avoid that. However, if you're like starting with a mammal-like animal and want to make it look weird, it's a pretty easy way to introduce design because there's no inherent reason you couldn't do this and simply give them more powerful, a more powerful ability to push off with their ankles is basically what that's giving you. Likewise, if you're starting with a dinosaur-like body and legs, there's no inherent reason you can't put a mammal-like smaller set of calf muscles on it to, again, start getting a mix and match feel to create a very different anatomy than what we see today or in our history. I'm not going to cover the forelimb muscles in too much depth aside from what I mentioned earlier with the lats and stuff, and we also covered some of it in the webinar, but we might slip into a little bit when we talk about hexapods next week. So, a brief review. Hopefully now, looking at this, you can see why I gave it these labels. This is, of course, the dewback again. And you can see it has that fairly dinosaur-like, very broad, triangular-like thigh. But notice that when it came to the calves, it was given a very skinny mammal-like set of calves, and also a mammal-like ankle bone, which we'll talk about in a little while. And so right here you can see how the dewback got a lot of sort of original design cred right away by mixing and matching that sort of design in the legs. And then, of course, the hips and the tail were more like dinosaurs or crocs. Hopefully you now know after a few weeks of discussion that this tail muscle is actually not lower enough. This should be an even bulkier and heavier and more flat-bottomed tail. But when this was done, she was probably looking at what was sort of common for dinosaur design at the time, and unfortunately that was an error introduced into paleo art back in the 80s and 90s that didn't go away until just about 3 or 4 years ago, and it's still sort of going away in some cases. Okay, some quick thoughts on snakes, and then I'll take questions about this section before going on. Someone asked about snake vertebrae. They are incredibly complicated, and they are complicated because they support an incredibly subdivided and powerful set of muscles. But the big thing here, the take-home message, I don't expect you to memorize all those muscles, obviously, is that snakes are not circles in cross-section. They're not even close. Snakes are actually very flat-bottomed. You can see it here in the underside of the snake. How flat-bottomed they are does depend to a degree on what kind of snakes they are. Snakes that spend most of the time in the water are not nearly as flat-bottomed. Some smaller grass snakes also are a little less flat-bottomed. They still are flat-bottomed, but they tend to be more flat-bottomed ovals. Bigger snakes, this may not surprise you, are even more flat-bottomed, not because they're heavier and they can't support the weight, but because they need more surface area on their bellies in order to better push themselves both around in trees and across the ground. I also want to point out that they actually have a similar contour all down their sides. It results, I'll show you in a second, in like long ridges. But these are that same set of back muscles I was telling you about, the equivalents of the iliocostalis and some of the other muscles leading up the spinalis and stuff, and the longissimus that we have and that we were talking about in dinosaurs. And it actually leads to a very distinct contour on the top of these guys for much the same reason the iliocostalis muscles are a distinct contour on everything else. Now, they don't have the equivalent of the lats because they lack forelimbs, but this is there, and I'll skip this. And you can actually see these ridges in living snakes quite obviously. Also, on the top of a lot of snakes, you'll see a muscular ridge. And again, although you can't see it too obviously, it's very flat-bottomed when you get down there. Now, I will say this. If you pick up a snake and look, and you don't turn it all the way over, the stomach does sag a little bit, and so if you have a snake and you pick it up, it'll look a little less rounded when it's actually going somewhere. And that, I mean, it's just kind of normal. If you were to pick me up by my, feet and my hands, I would also sag in the middle a bit and not really look like I do normally when I'm standing up. But I think that's where sort of the impression comes from, that snakes are like largely round on the bottom, is oftentimes people pick up or hold them, and it does sort of distort how they look. So here's another nice shot, and again you can see ridges on the top. You can also kind of see them on the side. It's a little less obvious in this lighting in this guy, where you have very distinct muscles. So you don't have nice extruded tubes or even just flat-bottom tubes. You actually have fairly complicated shapes when you have snakes. So we're going to go from there on to limbs, but I want to stop here to see if there's any questions so far on mussels or snakes.
Give us a quick shout out, guys. Just type yes if you've got a question in your type, and that way we know to wait until you respond.
I can't help but look at that cross section of the snake, excuse me, as like a Snickers bar. It's like a Almond Joy candy bar cross section. Like,
That one?
yeah, easy way to kind of remember their shapes.
Oh, that's really fascinating. Yeah, you're right. It really does. Yes, the ribs do. In fact, that's an excellent question by Charlie. You see those little dots here? Those are individual ribs moving through the cross-section. Here you can kind of see them moving back. Now, snakes, when they move on their ribs, the ribs can flex a little bit, so how much it's pulled back or closer to vertical does shift a little bit depending on where they are on their stride, but not a whole ton. That's a really good question. Is everyone pretty comfortable with what we've covered so far? Most of the muscles in snakes are axial muscles. So a lot of them have small sort of suborigins or insertations in different vertebrae or ribs going down, but I know there is a handover in the area where the pelvis used to be, which I think is about here in this guy, because of course snakes do have, or maybe, yeah, do have functional tails, maybe it's a little further back, and the rest is body, and there is a shift in the muscles between the two. Also, you can tell if you turn them over because they'll have their cloaca where they lay eggs and get rid of extraneous material they don't need anymore and make more snakes. And that actually is the easiest external way to tell. And I know there's a change off in origins there, and I don't actually know exactly how it works, so I'd have to look that up for you when we, maybe for next week. Maybe I could post about it in the forums. The back end of a ram, where does the snake go? Is it like a snake head and sort of neck on a ram's body?
Charles, you want me to unmute you? Do you have a mic? If anybody wants to talk, you can also try raising your hand too, and during these breaks I can just unmute you. Isan's got a question too.
Yeah, I believe the brachiocephalic is one of the mammal-specific names for a subdivision of what's essentially the sternocleidomastoid. Yes, and yeah, mammals have a sternocleidomastoid. Mammals often subdivide some of their muscles, and especially in veterinary anatomy, they'll end up renaming most of the muscles having nothing to do with the original muscle, which is really obnoxious. A snake's tail and a head at the end. I would probably, with that case, I mean, the snake tail is not going to be too hard. You're just going to give it a, I'd say, a thin, not perfectly round snake-like tail. You're going to have to widen the goat's pelvis a bit, make it a little bit more dinosaurian in that sense to make room for the tail, but otherwise you could probably, after widening the hips, blend the tail onto there, maybe with part of it coming up and meeting the back of the thighs a little bit. For the front end, I think you're going to have to go with, see, the Chimera has more than one head, right? because I think you're just going to want to basically do a snake's head and part of its body as the neck then, coming out of wherever it goes. You might, in that case, want to start out of the base, giving it something that would look like a sternocleidomastoid, actually, because a snake would undoubtedly have one if it actually had a shoulder region, which in a chimera it's going to. So one way you might want to like make it look more like it belongs on the body would be to keep a very snake-like head and have a fairly snake-like neckish region, if you will, but then add like that contour going back to where the limbs are. It's just a suggestion, but it might make it look more like it belongs there. If you want to give the snake wings, I would say you're going to want to leave obviously plenty of room for the neck, and you're going to want to assume that there is a set of scapula back here somewhere. You might even want to create sort of a sternum area that bows down a little bit so that you have room for like muscles, some of the flight muscles and sort of a pseudopectoralis. Otherwise, you'd want the scapula to curve up onto the snake body closer to the back, probably, in order to so it wouldn't move so much during flapping. Then you can have your wings coming out, however big you want. And then again, I would probably add some sort of a sternocleidomastoid type contour up to the neck. It could be pretty weak for as long as the snake neck-like feature isn't as muscular as it already is, but I still would add something to help tie it in with that now added on pectoral girdle. The movie Anaconda is not as far off as you would assume, but they are a little bit sped up to make them look a little bit more horrific. They are awfully fast in the water when they're flipping around. I'm trying to remember in the denouement with like the ridiculously oversized snake. I think it like wraps around people like insta-fast, and I'm pretty sure that's sped up a bit, but I'd have to probably rewatch it before I could really specifically critique the movie Anaconda. Also, despite what you've seen in the movie, anacondas don't preferentially look for people in bikinis. Alright, should we head on?
Let's do it.
Alright, enough snakes for now.